When you analyze a deterministic game like chess, you are looking at a finite mathematical space. A computer can read the board, map the branching tree of possible future moves, and muscle its way to an optimal decision through pure calculation. But Go breaks that computational model. A typical turn offers a branching factor of about 250 legal moves, and a full game runs for roughly 150 turns. That math produces 10 to the 359th power possible game sequences. For scale, there are only about 10 to the 80th power atoms in the observable universe. Calculating every path to the end of the game is mathematically impossible. If you can't reach the end of the game tree, why not rely on hardware? You run a parallel search on specialized chips, look a few moves deep, apply a heuristic evaluation to see who controls the board, and stop there. Because local heuristics fail in Go. In chess, a rook has a defined material value. In Go, placing a single stone on the left side of the board can dictate the survival of a massive group of stones 40 spaces away on the right. Algorithms built to count material advantage are completely blind to that global context. If exhaustive search is impossible and heuristic shortcuts are blind to the actual state of the board, we need a mechanism that searches deep into the game tree without wasting computational power looking wide. The tool for that is Monte Carlo tree search. Think of Monte Carlo tree search as a blind cartographer trapped in a fractal labyrinth. It has no map, no understanding of Go strategy, and no way to evaluate a board position on its own. It learns the environment in 4 repeating phases. First is selection. The algorithm walks down the path of moves it has already mapped. Once it reaches the edge of its known territory, it enters the second phase, expansion, adding one new, unmapped move to its tree. Since the algorithm can't evaluate if this new position is actually good, it enters the third phase, simulation. From this new node, it plays out the rest of the game making completely random moves until someone wins or loses. Finally, in the backpropagation phase, the result of that random game is sent back up the exact path it took. Every node along that sequence updates its ledger, recording one additional visit and logging whether that visit resulted in a win or a loss. Wait, simulation is just playing random moves until the clock runs out. How does simulating thousands of games of garbage play yield any reliable data for evaluating a high-level strategic position? One random rollout is pure noise, but over 10,000 rollouts, the law of large numbers takes over. The random, chaotic variables cancel each other out, leaving only the underlying probability of the starting node. If a board state gives you a dominant structural advantage, even a completely random sequence of legal moves will naturally stumble into a win more often than a loss. The win percentage from those random games becomes the node's true value. That explains how it evaluates a single node. But during the selection phase, when the algorithm is standing at a crossroad of 20 mapped moves, how does it mathematically decide which specific branch to explore next? This equation is the upper confidence bound, or UCB1 formula. It solves what mathematicians call the multi-armed bandit problem, balancing the need to exploit known advantages with the need to explore unknown paths. The left term is pure exploitation. You divide the total wins of a specific node by its total visits. This calculates the raw win rate. If a move has a high win average, this term pulls the algorithm towards selecting it again. The right term is exploration. It acts as a mathematical curiosity metric. It tracks the visits to the parent node against the visits to the specific child node. If a path is ignored, this term grows larger, eventually forcing the algorithm to investigate it. Why use the natural log for the parent visits in the numerator? Why not just use the raw count? Every time the parent node is visited, the numerator grows, which increases the UCB score for every single child underneath it. If you use a raw count, the exploration term dominates too quickly, and the algorithm will waste time infinitely checking bad moves. The natural log ensures the exploration pool grows, but grows painfully slow. And the square root over the entire right side? That is a geometric necessity to bound the variance of the confidence interval. As visits increase, the margin of error shrinks, allowing the algorithm to lock in its evaluation. UCB1 ensures no proven winning path is ignored and no optimal path is left underexploited. Vanilla Monte Carlo tree search is robust, but it carries a severe computational bottleneck. Running tens of thousands of random rollouts to the end of the game for every possible move takes far too long for real-time play at an elite level. AlphaZero removes the simulation phase entirely. It deletes the random rollouts and replaces them with an instant evaluation from a deep residual neural network. This diagram shows the network's dual-head architecture. The first output is the policy vector, denoted as P. It analyzes the board and instantly outputs a probability distribution of only the most sensible moves, immediately pruning the dead weight from the game tree. The second output is the value scaler, denoted as V. It looks at the board state and instantly generates a number between -1 and +1. It estimates the precise win probability without playing a single future move. That creates a logical paradox. If the neural network is powerful enough to instantly output the best move via the policy vector, why run the slow Monte Carlo tree search at all? Just play the move the network gives you. Because they represent two different types of cognition. The neural network operates purely on pattern recognition. It has zero capacity for forward calculation. The tree search provides the deliberate, forward-looking calculation needed to verify those patterns. AlphaZero does not replace search with intuition. It uses artificial intuition to guide a surgical, hyper-efficient calculation. The mathematical bridge that fuses the network's intuition with the tree search is the polynomial upper confidence trees, or PUCT, formula. Focus on the denominator in the exploration term, 1 plus the visit count of that specific action. What is the functional role of that as the algorithm runs through thousands of iterations? At the start of the search, the visit count is 0, so the denominator is exactly 1. Because of that, the equation relies heavily on the prior probability, the raw intuition provided by the neural network, to decide where to search first. But as a node is repeatedly visited and deeply calculated, that denominator explodes in size. As this graph shows, when visits increase, the entire exploration fraction collapses towards 0. The massive denominator crushes the influence of the neural network's prior intuition. All that remains driving the decision is the Q value, the hard, calculated truth discovered by the tree search over thousands of iterations. The denominator is the exact mathematical mechanism that allows rigorous, deep calculation to override a flawed initial intuition. All of this logic operates inside a self-play training loop. AlphaZero starts with randomized weights and plays millions of games against itself, generating its own ground truth data. After the search algorithm finishes calculating a move, the resulting distribution of visit counts forms pi, a deeply calculated, mathematically proven probability distribution of the best possible moves for that turn. This is the combined loss function. AlphaZero uses it to update its neural network's weights and minimize internal error. The first part is the value error. It calculates mean squared error, punishing the network if its predicted value outcome didn't match the actual end-of-game outcome. And the policy error term? Why use cross-entropy to evaluate the move choices? Because P is what the naive neural network instantly thought the best moves were, while pi is what the tree search proved after deep calculation. Cross-entropy mathematically forces the network's baseline intuition to mimic the results of the deep calculation. By continuously forcing P to match pi, the neural network absorbs the intelligence of the search algorithm. In the next game, the search starts with a sharper, smarter intuition. That allows it to calculate even deeper, which creates an even smarter pi. It is an infinite, closed-loop staircase of self-improvement, completely devoid of human bias.